Hey folks, welcome back to the third of part three of our standard model particle physics lessons, and this one is about fundamental forces. So we're going to look at how to describe how particles interact via force-mediating particles, state the four fundamental forces of nature, describe what the four fundamental forces of nature are and do, and state what a gut or GUT is. So first of all, how do particles interact? So what do I mean by that? Well, what I mean is how do electric charges know whether to repel or attract each other? How do masses know whether to attract each other? I'll have a pause the video, have a wee think, and then I'll tell you that we'll discuss this in the next slide. Now, hopefully you were able to tell me that, well, they can interact with each other via electric or gravitational fields. And remember, we've studied these already. We know that a gravitational field is important for masses to attract each other. We know that electric fields, there is a directionality involved with it, and there's also things called equipotentials. And you might remember how to calculate the kinetic energy due to the work done. And you could apply similar arguments to magnetic fields. You remember Fleming's right-hand rule and how a charged particle can experience a force in a magnetic field. So this is what we called the field theory. And we still use fields in physics, but there is also another interpretation. So in quantum mechanics, and we're going to study this topic in a bit more detail in the next kind of units, a mediating particle is associated with each force field. So instead of using a field to describe how these things interact, we say they actually use a particle. And this mediating particle transmits the force and is called a gauge boson. And again, you may remember this slide from a previous lesson, so we're now going to delve deeper into what these gauge bosons are. So first of all, in the standard model, we have our fermions, which are made up of our quarks and our electrons, or I guess you could call these our hadrons. And remember, these are fundamental particles. And then we have our bosons, and there are sort of 5 bosons: photons, a Z boson, a W boson, a gluon, and a Higgs boson. And these 4 here are called our force carriers. So you must be able to state what the 4 force carriers are along with the Higgs boson. So I would make a note of this in your notes. Now, what is a Higgs boson? And a couple of years ago, there was obviously a lot of kind of buzz about this because we're on the brink of discovering the Higgs boson, and we have kind of got evidence for it now. And so there's these 2 kind of video links, one by Minute Physics, which is very good, another explanation which just gives you a slightly different perspective. Again, you're not expected to know lots about the Higgs boson, but you do have to know how it kind of fits in the standard model and why it's important. It's important because it's responsible for mass. And you don't need to be able to explain what the Higgs boson is because it's a very difficult concept. So these videos are here just for your own personal reference. Now, how do particles create force? Well, first of all, again, you've probably seen this diagram before, but this is called a Feynman diagram, and it represents gamma radiation mediating an electron-electron interaction. So the idea of this diagram is that you have an electron coming in along this way, and you have an electron coming along this way in the opposite direction. And hopefully you remember when an electron meets an electron, they're both negative, so they repel each other. And this is why this electron goes off at an angle, and this electron goes off at the other angle. Now, we could explain this using field theory. However, we're talking about gauge bosons here. And the idea in gauge bosons is that these 2 electrons communicate with each other by sending gamma radiation. And that gamma radiation tells this other electron that there's an electron nearby and they have to repel each other. One way to think about it is the following. As you can imagine, if the electrons were replaced by skaters and that the gamma radiation was replaced by a bowling ball, as these 2 come across, or close to each other rather, they throw the bowling ball from one to the other, and that bowling ball has momentum, so that momentum can change the direction of the receiver. Now the person who threw the bowling ball will also change the momentum, so they will go off in another direction. And so this is how particles create force. So gamma radiation has momentum like a bowling ball. This is the analogy for how particles create a force. And I would expect you to be able to tell me a little bit about this analogy here. So make a note of that, and you may want to copy the diagrams as well. Now, moving on, what are the four fundamental forces of nature? So you need to be able to tell me what the four forces are. So I would again copy this table down in your notes. So we have the nuclear strong force, the electromagnetic force, the nuclear weak force, and gravitation. Now, the electromagnetic and the gravitational force, we've kind of studied those quite a lot in terms of G fields and E fields. And you can see that the range of these are technically infinite. So they go on for infinity. The strength of these now, how did we get the strengths? Well, first of all, if we look at the nuclear strong force, this has a relative strength of 1. So what we're doing to get the strengths of these is we're comparing all of these forces against the nuclear strong force. And the reason for that is, as the name kind of tells you, it's the strongest of the four forces. Although there is a proviso, it does depend on the situation and on the range. So what I mean by that is that the nuclear strong force acts over this range, so up to 10 to the minus 15 meters. Beyond that range, you can ignore the nuclear strong force as far as we're concerned. How do the nuclear strong force, how is it transmitted? It's transmitted by this particle called the gluon. And I'll talk more about the nuclear strong force in the next couple of slides. The electromagnetic force, as we said, is communicated or transmitted by the photon. So that's in the previous example of the electron interacting with the electron. Technically, it has a range of infinity, although really we know it only acts over small distances. If you think about, say, like an atom, the electrons in the atom can interact with each other, but they don't interact if they were very far away. And the relative strength compared to the nuclear strong force is 1 over 37. Now the nuclear weak force, again, I'll explain more in detail about this later on, but you can see this acts over a much, much smaller range than the nuclear strong force. It's also incredibly weak, which is why it's called the nuclear weak force. And it's mediated by these two bosons, W plus and W minus, or the said boson. Finally, gravitation. Really weirdly, gravitation is the weakest of the four fundamental forces. However, it does depend on the situation. Because remember, gravity is the thing that holds you to the ground. It's the thing that makes planets orbit around the sun. It's the thing that makes black hole exist. So when we say gravity is the weakest, we do have to say there's a reason for that. And the reason is gravity depends on how much mass there is. The more mass there is, the stronger gravity becomes. And this is why the sun can hold planets around it. It's because it's massive. The other really weird thing you have to think about is the range of gravity. So although it's really, really weak, it's actually got an infinite range. And if you think about it, again, it's the gravity of the sun which pulls the Earth into orbit. And remember, it takes light 8 minutes to reach us from the sun. So you can imagine how far away the sun is, and yet gravity is still able to act on us. So when you ask me which of these is the most strongest force, I can't really give you a straight answer. Now, I know I've given you a lot of detail there, so I'm going to try and give you some notes over the next couple of slides. Some of these things you can write down by playing back this slide again and then trying to write down some of the things I've said. Okay, so what is the strong nuclear force used for? So it mediates interaction between quarks and gluons, and as a result, it binds quarks together. And it's also used for binding protons to neutrons, because if you think about it, protons are positively charged, neutrons are neutral. How do they actually stick together? It's not like electrons and protons where you can argue there's an electromagnetic force attracting them. Here, it's not a charge, it's this gluon which glues them together. And that's why it's called a gluon, because it literally sticks things together in the atoms. Now, without the strong nuclear force, you wouldn't be able to have atoms, because an atom, if you think about it, is made up of a proton and a neutron. So these are combined together to give you the nucleus of the atom. So the strong nuclear force is really important for having atoms. Now, there are video links at the bottom here which go into this in a lot more detail. I'll provide you with these as part of your assignments. The weak nuclear force is the one that mediates interactions between quarks and gluons. So again, it's kind of linked to the strong force, and it allows radioactive decay to occur. In particular, it allows that beta decay to occur. So when we talked about how in beta decay a down quark converts into an up quark, it happens via this weak nuclear force. And again, there's another wee video there for you to kind of watch. In terms of notes, I would copy down what's there. I would do the same for the previous slide. I don't know if I said that. Using a diagram always helps as well. Now, the two other forces, gravity and electromagnetism, you've kind of done enough about these to know what gravity is. It's caused by the existence of mass, and it occurs around masses. It causes masses to interact with each other. Electromagnetism, you know it's caused by electric charge, and you know that like charges repel, unlike charges attract, etc. And here's the really weird things, folks. When we say the four fundamental forces of nature, what we mean is that these are the only four forces you need to create everything in the universe. And if you stand back and think about that, it's actually pretty amazing that there are only four forces that you need to make everything in the whole known universe. Now, towards the theory of everything. Now, this is a film that came out a couple of years ago, and it was about the very famous scientist Stephen Hawking. And one of the things that Stephen Hawking tried to do was he tried to find this grand unified theory, or GUT. So what is this grand unified theory? Well, here's a wee diagram which I quite like, and this shows you the different areas of physics. So here we have electromagnetism and gravity, which we studied. We've got general relativity, which you've done a little bit about. Now, Maxwell came along and combined the electric and magnetical and light theories to give us electromagnetic theory. And then, obviously, later on, we had the weak force and the strong force. And we know that the electromagnetic theory and the weak force are actually combined together in something called the electroweak theory. So this is on the small scale of things. On the large scale of things, we had Newton, who discovered or talked about planetary motion and earthly motion, and he combined these into gravity. And then we also had Einstein, who then revised Newton's idea and combined space with time to give us general relativity and gravity. And so at the moment, what we want to do is try to unify the strong force with the weak force, or the electroweak theory. And more importantly, we want to combine general relativity, which talks about the big scale things, with the small scale things. And this is where the idea of a grand unified theory comes from. Now, there are lots of possible theories which could be a GUT, and one of them is something called M theory. So again, there's a wee link here which explains it in a bit more detail. There is a lot of information here, folks, so your assignments will be about summarising the information that you've got here. I highly recommend you read your textbook, because there is a lot of really good information there about these different kind of ideas.